Pantev, who is going to speak about refine the parabolic stable pair invariants nested Hilbert schemes in MacDonald polynomials.
Thank you. So this is the title, and Ludmila actually said the long title. There are a few adjectives that are missing there, but it's too long anyway. So yeah, so this is part of a work in progress that I'm doing with Wuyang Chuang and Emmanuel Diaconescu and Ron Donaghy. And it's really about geometric engineering and constructing interesting geometric models for engineering two-dimensional theories. But the part of the story that I'm going to tell you about today, it's only one step in the whole project, and it's about a physics way of looking at character varieties for punctured Riemann surfaces. So I'll discuss this framework that allows you to approach the topology of the character varieties of punctured Riemann surfaces, which is a open problem in geometry, which has been the focus of a lot of interesting research. And it's surprising how such a simple object as a character variety has been resisting understanding for so long, and we still don't have well, we have some understanding, but certainly we don't have proofs of that understanding. So, and hopefully string theory really helps with that eventually. So the idea is that you are going to say something about the topology of those character varieties by identifying some kind of BPS invariants, which will be stable pair invariants on Calabi-Yau threefolds. And for the puncture case, they cannot just be Calabi-Yau threefolds, they will be Calabi-Yau threefold stacks. And you'll identify that with some kind of partition function in an omega background, in a four-dimensional gauge theory. And that will allow you to say something about the topology of that character variety. And the whole procedure is based on wall crossing formulas for parabolic sheaves on a Calabi-Yau threefold, which are representations of the ADHM quiver. And at the end of the day, of course, you want to get something about the topology of the character varieties, which will appear in our understanding as in a different complex structure model as the tamely ramified parabolic Higgs bundles. So that's what I'll try to explain. Now let's start. So the goal at the end will be to actually verify these conjectures that actually describe the topology of the cohomological invariants of the character varieties or the Higgs bundles completely. So it's a conjecture of Hausel, Letelier, and Rodriguez-Villegas. And so we can use this whole formalism to say something about that conjecture and verify it in particular cases. Okay, so here is the setup. We're dealing with ramified character varieties of a Riemann surface. So you start with a smooth projective curve over the complex numbers of some genus. You have a reduced divisor, which will be the punctures in our Riemann surface with k points. And at each puncture, we'll fix some data. The data will be just a diagonal R by R matrix. And since we're looking at representations of fundamental groups, you need to, well, it's useful to impose this condition, which I'll impose, which is that the product of the determinants of those matrices is 1. Now, with this data, you have some numerical invariants that you can attach. With each diagonal matrix, you have a companion partition, which just breaks R into the multiplicities of the eigenvalues. You have the conjugacy class of the diagonal matrix, and I'll write both point mu and both point c for the conjugacy classes over the whole divisor and for the partitions over the whole divisor. Okay, and then once you fix that data, you get a moduli space, which is the character variety. It is the space of all representations of the fundamental group of the punctured Riemann surface into the general linear group of R matrices. You want to impose conditions on the local monodromies, so you want your representations to send a loop around each puncture into that conjugacy class. And so you see that that condition on the determinant is necessary if you want to study this representation variety, just because the presentation for the fundamental group is given by A cycles, B cycles, and these gamma cycles. And there is one relation which says that the commutators, the products of the commutators times the gamma cycles is the identity. And the commutators, of course, have trivial determinants, so the product of the determinants of the gamma cycles will have to be trivial. And so you do this modulo conjugation, and you get this. So you take the affine GAT quotient. This is an affine variety, the space of all such rows, because this is a free group. And you mod out by an overall conjugation, and you get the character variety of type C. And maybe, okay, so I don't know how to go to my, well, okay, let's see. So there is a theorem due to Hölzel, Letelier, and Rodriguez-Villegas, which says that for a generic choice of the conjugacy classes C, this moduli space is a smooth affine variety. It could be empty, but if it's not empty, it has the expected dimension. The expected dimension depends only on the partitions, doesn't depend on the particular eigenvalues, and it's given by this number. So it's R squared times 2G minus 2 plus the number of punctures, and then you have to subtract the centralizers of each conjugacy class, the dimensions of the centralizers of each conjugacy class, which you can write in terms of the partitions, and then there is an overall correction by 2. So these are nice varieties. They're affine algebraic varieties, which are nice and smooth, and are given by the representations of one group, which is explicitly written by generators, and one relation. And it's amazing that we don't really know as much as we would like to know about these varieties. So maybe let me just say what generic means. So I guess I can just click here. So generic means that if you choose elements in those conjugacy classes, and you look at an invariant subspace for those elements, and you require the same condition that the determinant of the restrictions of those elements on the invariant subspace multiply to 1, then that invariant subspace has to be trivial. It's either 0 or everything. So that's the genericity assumption. And so it's some kind of a stability for these representations of punctured Riemann surfaces. And you can check that generic collections always exist. So that's the genericity assumption. And what's the next one? Okay. Okay, so once you have that smooth affine variety, you can try to compute its Betti numbers or its Poincaré polynomial. You can do it for the cohomology or for the compactly supported cohomology. And you can do it intelligently, trying to remember as much of the structure of the variety as you can. So you can actually work with the Hodge numbers for the mixed Hodge structure on the cohomology of this affine variety, and write down the mixed Hodge polynomial. What we're doing is slightly less than that. We're ignoring the Hodge numbers, so we're not looking at the Hodge filtration at all. We're only remembering the weight filtration. And we're writing the mixed Poincaré polynomial, which just computes the associated graded pieces, the sizes of the associated graded pieces of the cohomology, compactly supported cohomology with respect to the weight filtration. and then you weight it by, you put it into a counting function, into a counting polynomial. There is this, the thing that counts the weight, because the weights are even, you want it to be given by a power of a variable which is a square root of a formal variable.
That's a motivic invariant.
It's some remnant of the motivic invariant because it remembers about the topological part of the motif, which is the weight filtration.
But it is motivic in the sense of being additive.
Yes, it's certainly, yeah, it's additive in the ring of motifs, but you know, it's much less information than any motivic invariant that you would write, because only remembers the weights, doesn't remember any finer information. Yeah, so you would like to compute that, and that's the goal. And so this conjecture I was talking about of Hausel, Leterrier, and Rodriguez-Villegas actually gives you a formula for this weighted Poincare polynomial. So you take a sequence of infinite sequences of formal variables, so I call them bold-voice font x1, x2, and so on. And then you look at the generating function for those Poincare polynomials. So you weight them with some explicit rational factors in formal variables z and w, and then some monomials in the counting variables. So we denote it by f because in physics it will appear as a free energy function, so we'll call it the HLRV free energy. But it's really the platistic generating function of all those Poincare polynomials for all possible numbers of generating points. You see it's punctures, you know, it's summed over all k's and all possible conjugacy classes. Partitions. I mean, it only depends on the partitions. Okay, so you have this function. These are just the monomials that are determined by the partitions. And as I said, we call it the free energy function. And then the formula that conjecturally computes this thing was intelligently described by Hausel, Leterrier, and Rodriguez-Villegas from some arithmetic considerations. And it's comparing it to something which I've written here. It's a function, again, on the same variables. And it's a sum of polynomials where the h twiddle lambda are the modified MacDonald polynomials, which have a purely combinatorial description in terms of Catalan numbers. I'm not going to write down the combinatorial description. I'm going to write down the geometric description in a moment because that comes from the work of Hyman, because that's what's relevant for our discussion. But so these are some explicit polynomials. And then a rational function in z and w that's determined by a partition and the genus G. So the genus G, you see, the free energy function, which was computing the moduli, the Poincare polynomials of the character varieties, depended on the genus, right? We allowed the punctures to grow to infinity. We allowed arbitrary conjugacy classes, but the genus was encoded in there. So in this function, you also have the genus G. It appears as a power there. And it's a product over boxes in the Young diagram of the partition and the polynomials appearing in the numerator and the denominator have powers coming from the arm and the leg length of the box in the Young diagram. So this is some completely explicit combinatorial expression, and so we'll call this the HLRV partition function. And the conjecture that Hausel, Leterrier, and Rodriguez-Villegas made was that this partition function is the exponential of the generating function for the Poincare polynomials. And so in particular, it gives you a complete answer for the Poincare polynomials of the character varieties if you know it's true. And they ran numerical tests to check that it's true in groups of low rank and few punctures when they made the conjecture. This is the plethistic exponential. You really need to take the exponent in the lambda ring, but that's not that important. So the way we want to approach this conjecture is maybe before, well, okay. The way we want to approach it is by interpreting both sides of the conjecture physically. So we want to take the partition function and the free energy function and deconstruct them in some specific way by thinking about them as counting functions for BPS states or some other types of interesting vacuum states in some physical theory, and then use physical dualities or geometric dualities to relate the steps of the deconstruction one to another and eventually go from the left to the right or from the right to the left. So that's the plan. How do you decompose this identity of two counting functions into a sequence of identities, each corresponding to a particular either geometric or a string theoretic duality? And specifically, the plan will involve to interpret the formula as a refined BPS expansion of a Gopal-Kumar-Vafa type for a stable pair theory on some Calabi-Yau threefold. So right now there is only a curve in the picture, but the idea is that there is going to be a Calabi-Yau threefold. We'll be counting refined BPS, refined invariants and their BPS expansion, and that BPS expansion will give you that exponential formula. And once you have this interpretation, you can try to use your interpretation to actually verify the conjecture, at least in some cases. Okay, so that's the goal. So you need to have some geometric interpretation of all the pieces that appear in this partition function or free energy function. Okay, so first of all, in the partition function, we had this rational function, which was the Hooke polynomial, the deformed Hooke polynomial, the one that was given by the explicit formula with the arm and the leg lengths of a box in the partition. And in a previous paper, Chuang, Iaconescu, and Pan actually gave a geometric interpretation of this by using physics argument. And the geometric interpretation uses the Hilbert scheme of R points on the plane. So you take the Hilbert scheme of R points on the plane, and you construct a bundle that depends on the number G. It's going to be the cotangent bundle of the Higgs-Hilbert scheme, and you're going to add to it a line bundle into a power 1 minus G. And the line bundle is just the determinant of the tautological vector bundle on the Hilbert scheme, which is the push forward of the structure shift. So it's the tautological rank on R vector bundle, the push forward of the structure shift of the universal zero-dimensional scheme parameterized by the Hilbert scheme. And then the geometric interpretation of these rational functions that we wrote is that if you add them up with some monomial weights, depending on the partitions, overall partitions, you get the equivariant, the T-equivariant Hirzebruch genus of that vector bundle. Right? So that's an equivariant vector bundle on the Hilbert scheme. The two-dimensional torus that acts on the Hilbert scheme that acts on C2 acts on the Hilbert scheme. And if you compute the T-equivariant Hirzebruch genus and do a change of variables, so if Q1 and Q2 are the standard variables in the characters of the torus, you do this change of variables and you get these deformed Hooke polynomials. So they appear in this extremely natural way geometrically from the Hilbert scheme. Okay. Now, maybe I didn't say anything about the MacDonald polynomials, and they are somewhere here. so maybe before I jump to the other side of the conjecture, let's finish with the partition function. So let me just say, so the MacDonald polynomials, they were described geometrically by Hyman, and the way they appear, again, they appear through the Hilbert scheme of points, of R points on C2. Right, so the geometric interpretation is you look at the isospectral Hilbert scheme, which is the fiber product of the Hilbert scheme and the set of ordered R-tuples of points in C2 over the symmetric product. And you take the reduced isospectral Hilbert scheme. So it's a scheme. It actually has nilpotents, has embedded points. So you reduce it, and then Hyman checked, and it's a deep and very interesting theorem, that it's a normal, irreducible, and Cohen-Macaulay variety, this reduced isospectral Hilbert scheme. And then the MacDonald polynomial appears, again, as a counting function. So you look at the map from the reduced isospectral Hilbert scheme to the Hilbert scheme, push forward the structure sheaf, you get an equivariant vector bundle of rank R factorial, equivariant for the action of the symmetric group, and it's also equivariant for the action of the torus. And then the T fixed points are, of course, the monomial ideals, so they're labeled by partitions. And if you take a monomial ideal centered at the origin and decompose the fiber of that vector bundle at that point under the symmetric group, you get multiplicity spaces that are representations of the torus. And so if you sum over all representations of the irreducible representations of the symmetric group labeled by partitions, the multiplicity spaces, these V lambda mu's, are going to be representations of the torus. And then Hyman showed that this MacDonald polynomial is the equivariant Chern character, T-equivariant Chern character of those T-equivariant vector bundles weighted with the Schur functions. And those are viewed, with, of course, as representations of the torus, so that's why they are Laurent polynomials in Q1 and Q2. Okay, so going back to the other side, so this gives you a complete description of the left-hand side of the formula in terms of either the isospectral Hilbert scheme. One piece is coming from the isospectral Hilbert scheme, the other is coming just from the Hilbert scheme. Now, the right-hand side is more complicated. And because it has to do with the character variety. And the way to approach it is by using a different complex structure on the character variety, which is the moduli space of parabolic Higgs bundles. So the non-abelian Hodge theorem identifies the character varieties of these punctured Riemann surfaces with moduli spaces of tamely ramified parabolic Higgs bundles, but only up to diffeomorphism, so not as complex manifolds. So the character variety, so I'll look at a slightly different and better behaved, twisted version of the character variety where one of the conjugacy classes has been isolated and it's central. So I took, generic conjugacy classes. In fact, this generistic assumption on the conjugacy class that I wrote, if you write it for a central conjugacy class, it just tells you that the eigenvalue is generic. It has irrational slope, or if it's a root of unity, then it's a primitive root of unity. Yeah.
If you're using a C infinity identification,
Mm-hmm.
Does this mean that this method cannot give you a mixed Hodge data or more general motivic?
You mean beyond the weight filtration?
Or beyond the volume of the Poincare polynomials?
No, it gives you information. So I'm coming to this point. It gives you more than the Poincare polynomials. It gives you these mixed Poincare polynomials which have more information. It's still topological, but if you want to input, more motivic data, then there is no hope. But yeah, it's interesting, and I have no explanation. I mean, I'll come to that in a moment. It's interesting that we are using a C-infinity information. We're trying to extract some motivic data, piece of the motivic data, and we actually do get a piece of the motivic data that's visible through that C-infinity identification. And it's a complete mystery of why that's the case. Yes?
The time I can ask, you just described one side of your formula as coming from the Hilbert scheme and the isospectral Hilbert scheme.
Yes.
Where is the data of the curve?
There is no data of the curve. It's just appearing as the genus. Right? In the description of the one coming from the Hilbert scheme, the vector bundle, there was the genus appearing there. That's the only way the curve. Of course, all the curves are equal in the world of character varieties. So only the genus matters. But yeah, so you fix. So instead of taking product of commutators, product of local monodrome is equals the identity, you take product of commutators, product of local monodrome is equals a central element in GLR. That's the only difference. And you get a moduli space of parabolic Higgs bundles. So this is a vector bundle E of rank R. Meromorphic map from that vector bundle to the vector bundle tensor with the canonical class with poles at most at P. And there is a little bit of extra data. There are flux. So I'll come to that in a moment to spell it out. There are flux in the fibers of that vector bundle specified at each point. The residue of that meromorphic Higgs field is supposed to preserve those flux. Will require that the residue is nilpotent, and then there's some real numbers, alpha, that you attach to each step of the flux, which are the parabolic weights. And once you choose this decoration data, the flux and the real numbers, it turns out that there is a way to identify those two smooth manifolds as C-infinity manifolds. Of course, you have to choose your flux and your alpha data in correspondence with the data of the CI and beta. So let me say how that's done. So as I said, the bundle E is of rank R. It has some degree E. At each point, we specify flux of some length, Si. The dimension of the steps in these flux, so the graded pieces, are called Mi. And then for each Mi, there is a real number, which is the weight of that Mi, the parabolic weight of the corresponding step of the flux. And these numerical invariants match under the non-abelian Hodge correspondence. So if you write your diagonal matrices with entries lambda on the diagonal, they are purely imaginary, given by the alphas. They have phase alpha, which are the parabolic weights, and beta is just the parabolic degree. It's the sum of the degree with the parabolic weights weighted with the multiplicities. And so this is, I mean, you can do these parabolic Higgs bundles in a much bigger generality when you don't fix, you don't require that the residues are nilpotent, and then you'll get twists of the character varieties, which are much more complicated. But if you just want the character variety, this is what you get from the Higgs world easily. I mean, you could take the diagonal entries in the CIs to be not to be on the circle, but to be arbitrary non-zero complex numbers. but then you have to remove the condition that the residues are nilpotent, and the picture becomes more complicated. And in fact, the geometric framework that I'm describing is kind of mysterious there. We haven't quite figured out how to do it. Okay, but so this is how they're matched, and this is a homomorphic symplectic manifold, which is a completely integrable system. There is the Hitchin map, which sends a Higgs field to its characteristic polynomial. The fibers of that map are abelian varieties, and they're Lagrangian in that moduli space. And now we come back to Dominic's question. You can recast the mixed Poincaré polynomial of the character variety as a refinement of the Poincaré polynomial of the Higgs moduli space by using the Hitchin map. So there is this amazing conjecture, P equals W, of the Cataldo, Halsell, and Migliorini, which says that if you take the mixed Poincaré polynomial of the character variety, it's a refinement of the Poincaré polynomial of the Higgs moduli space, and it's refined again in the same way by writing a filtration on the cohomology and taking the weighted pieces of that filtration, the dimensions of the weighted pieces of that filtration. And that filtration is the perverse Leray filtration for the Hitchin map. So you take the constant sheaf on the total space of the moduli of Higgs bundles, you push it forward, you get some perverse sheaf on the Hitchin base. The Leray filtration gives you a filtration on that perverse sheaf by using the middle perversity. And if you take the cohomology of that perverse sheaf, which is the cohomology of the total space, and you filter it by the perverse Leray filtration, and you weight, you should get the same thing as the weight filtration on the other side of the non-abelian Hodge correspondence. So Halsell, De Cataldo, and Migliorini discussed this in the non-ramified case, and in fact proved it for SL2 by an explicit calculation, because there everything is known about the moduli spaces going back to the work of Hitchin. So going deeply into the structure of the Hitchin map and the weight filtration on the character variety, they were able to prove that for SL2 with no ramification. But the conjecture makes sense for any group, and they made it for any group, and it makes sense also with punctures. So you can actually write this motivic refinement of the Poincaré polynomial by using the Hitchin map now, which is part of the motivic structure. I mean, it seems like extra data on the Higgs moduli space, but it's not. It's part of the motivic structure of the Higgs moduli space. It's actually the affinization map on the Higgs moduli space. So it's completely intrinsic. So you use this to actually rewrite the Poincaré polynomials we were interested in the language of Higgs bundles. And now we can do the reductions. We can look for our Calabi-Yau and our BPS invariants. So the idea is that if you start with the quasi-parabolic data, oh, my M is missing. So the quasi-parabolic data was the data of the points, the punctures, and you have to specify the steps in the flux at each point. There were these MI numbers, which are missing in my slide. So you fix that data. So the length of each flux was SI, and that gives you actually an orbifold curve, which is you take the open curve and you glue a Stacky disk to the open curve, which is just the quotient of the disk centered at pi modulo the roots of unity of order SI acting. And so it's a Stacky curve. It looks like C everywhere, but at the punctures, you have added the classifying stack of the cyclic group of order SI. And it has a coarse moduli space, the original curve C. And now you have a structure morphism from the stack to the coarse moduli space, and it sends a homomorphic Higgs bundle on C hat to a quasi-parabolic bundle on CP and M. And in fact, there is a theorem that was proven in various guises by many people, probably more than I've written there, which says that the category of homomorphic Higgs bundles on C hat is equivalent to the category of parabolic Higgs bundles on CP-M, quasi-parabolic type M, with parabolic weights given by just integers modulo Si, and nilpotent residues. And so this is crucial, that nilpotent residues, which was one of the conditions I imposed, or circle-valued conjugacy classes, which was the equivalent condition, this has this geometric interpretation in terms of the Stucky curve. And that equivalence of categories actually respects stability. Now, one thing we check is that the category of parabolic Higgs bundles on this punctured curve with those types of weights and nilpotent residues is equivalent to the category of spectral data on the total space of the cotangent bundle of that curve. And that equivalence also respects stability. Okay, now this is the good news, because what it tells you that you can think about these parabolic Higgs bundles with nilpotent residues as spectral curves sitting inside this surface, which is an orbifold surface. It has isolated orbifold points. And line bundles on top of those spectral curves. And this Stucky surface is symplectic. It's homomorphic symplectic, and in fact, it's hyperkähler orbifold. So you can consider a Calabi-Yau threefold, which is the product of that Stucky surface and a line. And you get a non-compact Calabi-Yau threefold, which happens to be a stack. And so you can hope to relate somehow the spectral data on your surface to configurations of branes on that Calabi-Yau threefold in the type 2A theory. And so that's the stable pair. So the BPS states for that type 2A theory are the stable pair moduli problem. So you have this Stucky Calabi-Yau threefold, which is the total space of a rank 2 vector bundle with canonical determinant on the Stucky curve. It's just K plus O. So, an analog of that will be the, if you take C to BP1 and no punctures, a typical example of this will be, you can take any sum of line bundles or any vector bundle with canonical determinant to play this game. You can take the conifold, the resolved conifold. But here you're just taking this guy. And now you're looking at the moduli problem of pairs, F and S, where F is a coherent sheaf on Y, whose support is finite over the curve. Y projects to the Stucky curve. Then you have a map from the structure sheaf to F, and the support of the co-kernel is zero-dimensional. So these are these Pantev-Thomas stable pairs. And the discrete invariants here are the degree of the support of F over the curve, which is R. And then there is the Euler characteristic of F, which by using Kalima-Roch shift, you can write as the degree E, which is going to be the degree of the Higgs bundle. And then there are some points Mi, some integers Mi, which remember how this stable pair interacts with the Stucky points on the surface or on the threefold. And they are these quasi-parabolic data integers Mi, which in this language, in this picture, appear as fractional brane charges. Okay, now this, the refined stable pair invariants that will be relevant for the HLR-V conjecture, they count the stable pairs on Y, and they can be organized in a generating function, in a partition function, weighted by monomials in Q and some variables xi. The coefficients are these Pantev-Thomas stable pair invariants, and those are obtained by virtue of Poincaré polynomial specializations of the motivic, of the conjectural motivic Kontsevich-Soibelman invariants. So again, there are a lot of steps in this formalism that haven't been proven, but the formal properties that we have are enough to say how these refined invariants behave. And in some cases, so like Sheldon and Albrecht Clem, they have actually computed them and constructed them rigorously. So now you can make reductions. The partition function, the HORV partition function, you can identify by embedding this stable pair theory for type 2A into M theory and then doing a type 2A M theory duality. You can identify the partition function for the refined invariants with the partition function for the refined invariants on the curve C hat cross the plane on this threefold, which is not a Calabi-Yau threefold. And then there, once you write down the branes, you get the moduli space for this Pantev-Thomas invariants turns out to be the nested Hilbert scheme for the plane. And then you can write down actually an explicit vector bundle on the nested Hilbert scheme whose cohomology computes exactly by using the interpretation in terms of Hilbert schemes of the HORV partition function. You can get it. There is a little subtlety which I don't have time to explain, and I don't have slides to explain it, so I'm not going to explain it, about the obstruction theory on this nested Hilbert scheme. So the explicit vector bundle that we write that computes it doesn't seem to come from any obstruction theory, but what happens is, and Andrei Okunkov actually explained this to us, is that there is a natural obstruction theory on the nested Hilbert scheme, and there is a natural obstruction which is coming from the fact that the nested Hilbert scheme behaves like a local complete intersection. And there is a natural obstruction theory on the stable pair moduli space. The moduli spaces are the same, but there are two natural obstruction theories that appear. And if you compute the difference of these two natural obstruction theories, you get exactly our bundle that computes the HORV partition function. So you need to make a change of variables in order to match those. And the other reduction is that if you make the same change of variables and use the P equals W conjecture, you get an identification of the HORV partition function with the partition function for the perverse Poincare polynomials of the moduli of Higgs bundles. And then you just need to relate the perverse Poincare polynomials for the moduli of Higgs bundles to the counting function, to the partition function for the stable pairs on that Calabi-Yau threefold. And this is where the spectral correspondence comes into game. There is a wall crossing. The stability condition for those stable pairs depends on a parameter. And if you compute the wall crossing, so if you look at the regime in which that parameter becomes infinity, the stably stable pairs actually become literally Higgs bundles. So you can actually use wall crossing to identify one partition function with the other. In order to actually match with the particular perverse Poincare polynomials, you need to do a Gopa-Kumar-Vafa expansion along the fibers of the Hitchin map, which is coming from the SL2 action along the fibers and a C-star action on the Hitchin base. But it works. And then, so this is how you reduce one side of the HORV formula to the other through a sequence of geometric dualities or string dualities. And then you can try and check some of those steps. So this, because one step is a purely string theoretic duality, which we don't know how to compute. And there is also this step that uses the motivic Dorns and Thomas invariants, which again, you don't always know they exist. So there are a lot of, and the P equals W conjecture. So there are several deep conjectures in between that make this comparison possible. So you can try to check, at least in some cases, whether this makes sense. And so we check directly that the stable pair invariants are exactly the HLRV partition function. If you take C to be P1 and you have one parabolic point. And this uses virtual localization and this formalism of Nikita and Okunkov, which describes the refined invariants in terms of K-theory localized invariants. But it actually gives the precise formula that I wrote with the change of variables in this case. And you can also check the wall crossing relation between the two partition functions. Okay, I think I'm done, and everybody's hungry, so I'm going to stop.
Any questions? Could you say a few more words about the hypercaret surface that you obtained?
It's a Kuiper-Keller orbifold. So you can, the simplest case, I mean, if your static curve is a global quotient of some curve by the action of a finite group, then you can just take the cotangent bundle of that curve and quotient it by that same finite group, and you'll get an orbifold, which is your Hypercaler surface.